So what I want to do now is I want to go through an example of a design of a flocculator. Okay. So what we have is we have a cross-flow horizontal shaft paddle wheel flocculator. So what that means is, think about it this way. We have cross-flow. We have a center shaft here. And on that center shaft, we have a paddle wheel. Okay. And if we looked at the paddle wheel this way, what we really have is, well, we have this. Okay. So we have 4 arms in this case of the paddle wheel. These are the arms. And on the arms, we have blades. Okay. And if the blades look, so we'd have blades like this. So these would be the blades on the paddle wheel. Okay, so it's cross flow because the water is flowing across. You can see it this way. Okay, we could arrange it the other way, but we're going to do it with a cross flow. Now we have a total flow rate. So this is our design flow rate. We need to provide redundancy. What we will do, okay, in this case, what I'm doing is I'm dividing the flow into 2 basins. However, we have 2 basins, and I'm dividing the flow. The GLIM standards requires that I have to be able to produce water with 1 treatment train out of service, or 1 unit out of service. So in that case, really what I need is I need a 3rd basin, so that, for instance, if this basin is out for maintenance, I can still use these 2 basins, and I still can meet this design flow. The detention time that I'll use is 45 minutes. That comes from my jar test. And my G times time, so this is the G value times the detention time, should be between 50,000 to 100,000, and this is based on the 10 state standards for low turbidity, where what we want is color removal. So we want, if we had a different water characteristics, we would have to change G. So for instance, if we had highly turbid water, we would have to increase G according to the requirements of the 10 state standards. If you're operating in the Midwest, if you're operating elsewhere, there are other standards, or you may, as I mentioned, the state or countries may actually adopt the 10 state standard. These values here are all obtained from the jar test. So the jar test was done, okay, and that's how we obtained or determined tapered flocculation. Now, often what we have is we have multiple compartments in a series. So we would have another compartment here. So this would be a 2nd compartment. And the reason we do that is as we're forming this flock, it's getting larger. And as it gets larger, if we maintain a high G value, the flock tends to break apart. So if the flock breaks apart, so if we end up with smaller flock particles and the flock breaks apart, so we have too high G and the flock breaks apart, what happens then to settling? It decreases, exactly. So you see a decrease in efficiency, then you And as just was asked, if the flock is breaking apart, the G is too high. So what we do in order to try and minimize the flock breaking apart like this, then what we'll do is we use what's referred to as tapered flocculation, where we decrease the G value from one compartment to the other. So this is actually a baffle here that allows, so the flow is allowed to move through here, but it moves through slowly. It could be a perforated wall with holes in it. It could be a wall with slits at the bottom, typically at the bottom, that allows flow through, but at a slower rate. It could just be a slotted wall, essentially a slotted wall that allows flow through. So you've got flow through here. In this case, we would have a G value of 50 inverse seconds here. And then in the second compartment, we would have 20 inverse seconds. And then we'd have a third compartment here. We'd have a third compartment here with 10 seconds. Okay. So we have this third compartment here. We have flow through here. And this is just the average G through all the compartments. So we're going to set this, and some of this was stipulated in the description that's in the PowerPoint, but we'll use a width of 15 meters. That was set. So this was set in the design criteria, and it was to combine with an adjacent sedimentation basin. The speed of the paddles relative to the water, we're going to set at 75%. That's very typical. And the temperature is 10 degrees C. So we're designing it for water that has a temperature of 10 degrees C. The average, this is the average GT value, is 26.7 times the 45-minute detention time times 60 seconds per minute, and that gives us a value of 72,000, roughly 72,000, and that is right between the required values of range of 50 to 100,000. So the next thing we need to do is determine the basin volume. So the volume of our basin is equal to the 25,000 meters cubed per day, 24 hours per day, 60 minutes per hour, and we have a 45-minute detention time. That's what we specified based on the jar test. And that means we need a basin that has a volume of 781 cubic meters. The width, as I mentioned, was set at 15 meters. That was to align with an adjacent sedimentation basin. And a rule of thumb, and you'll see this throughout the designs, of course, we'll talk about rules of thumb. It's just based on experience. The depth should be between 3 and 5 meters. So let's pick a depth to start with of 4 meters. We have to start somewhere. So in that case, we determined the volume based on our detention time and the flow rate. This is our width and our depth. So we can determine the length, and that is 13 meters. Now, each basin is 13 meters is the total length. So if we're looking again at our flocculation basin, the total length is 13 meters. We have 3 compartments. So the length of each compartment is then 4.34. In order to provide design specifications that can be met, we're going to round off and we'll only use 1 decimal place. So if our length is 4.3 meters, so we've just rounded off. We could round up or down, but we rounded down, times 3, so it's 12.9 meters. So instead, when we round off, this is not going to be 13. This is actually going to be 12.9 meters. The volume is 12.9 meters then, times 15, the width, times the depth. And so it is actually 474 meters cubed, so it's slightly less. So notice, we determined the volume. We then calculated the length. We then made a engineering judgment on what was a reasonable design specification. So we go from 4.34 meters to 4.3 meters. That gives us a new length, which gives us a new volume, which is the actual design volume. And then our detention time is still 45 minutes. Okay, so we really haven't changed. We haven't changed the detention time significantly by that change. Now, each compartment has a volume of 4.3 meters times 4 meters times 15 meters. So the actual volume of each compartment, not quite sure what I said, Elizabeth, but yes, the new volume. So this is our the new volume is equal to 4. Is equal to your is equal to 774 cubic meters. Thank you. This is 774. Assuming a depth of 4 meters, the surface area of each compartment is 64.5 meters squared. So now we need to go actually and size the paddle wheel itself. So we've got a basin depth of 4 meters. We've got a design criteria that the depth of the basin needs to be 1 meter greater than the diameter of the paddle wheel. So it's the bottom of our basin. Here is the water level. And this is the depth of the water. So we're actually calculating with all of this is the depth of the water. There's actually, if we were to build this, there's actually what we call freeboard. And that's about 0.6 meters. Basically, you want some volume of the tank above the water level because you don't want water splashing out onto the deck of your tank. So we have a paddle wheel here. So that's our paddle wheel. We need to have 1 meter clearance, and so we need at least 0.5 meters above, and we need at least 0.5 meters below. So we need that 1 meter. So we can make the diameter 3 meters. Okay. So this was the 4 meters depth minus the 1 meter clearance that we need, and that gives us a 3 meter diameter. The next thing we need to think about is the minimum length of the stage has to be the diameter of the paddle wheel plus a design criteria of 1 meter minimum between the stages. So back looking here, okay, we want 1 meter. So well, let's go back here. Here is the next paddle wheel, and we want 1 meter between the stages. And so we had a minimum length, then the diameter. So the diameter is 3 meters. We need a 1 meter minimum between the stages. So the minimum length is 4. We have a length of 4.3 meters. This is the actual length. So we've met that criteria. The design specifications state that we have 4 paddle wheels per shaft. And this is given in the specifications. Okay. So the way that I drew this, back here I only have 2 on the shaft. So this is your center shaft. This is shown with 2, but we would have 4. So we have 4 paddle wheels per shaft. The required clearance is twice the minimum clearance. So let's look. We'll draw this. So this is the wall here, and this is our shaft. So we have 1, 2, 3, and 4 paddle wheels. Okay. The minimum clearance from the wall is 0.3 meters. And then it is 1 meter between each. So the required clearance is 0.3 times 2 plus 1 meter times 3. So we have 3.6 meters. You'll notice when you'll need to do a similar design for the design project, I will give you a certain amount of specifications, but you're going to have to make assumptions, and it's an iterative solution. My advice is set up an Excel spreadsheet, because you're going to want to change the sizes of your units. You're going to want to change the sizes of your flocculation plates, and it's much easier to do that on an Excel spreadsheet than it is to do it entirely by hand. Okay. So we have these 4 paddle wheels per shaft. If we initially assume, so we're going to initially assume that the length is 3 meters. Okay. That's an initial assumption. And then we have 3 meters times 4 blades plus this 3.6 clearance. That gives us 15.6 meters. But remember, the width that we specified was only 15 meters. So we can't fit this into this 15-meter width. So we need to specify we need to reduce the size of the length of the blade, or the length of the paddle wheel, and we can take 15.0 minus 3.6, divide by 4, and the length of each paddle wheel is 2.85 meters. I'm going to leave that at 2.85. These are redwood slats. You can cut a redwood slat to 2.85 meters. So just to reiterate what we have flow in, and this is our profile view. We have a water level here. We have 3 compartments. We have a paddle wheel in each compartment. Okay. And the radius of the paddle wheel, the diameter of the paddle wheel is 3 meters. Okay, so that's our diameter. The plan view looks like this. Again, we have 3 compartments. The G value starts at 50 inverse seconds in the first compartment, 20 inverse seconds in the second, and 10 in the third. We have a center shaft in each, and we have 4 paddle wheels on each, and the length of this paddle wheel is 2.85 meters. Okay, so we've said this is what we've stated. We've got 4 paddle wheels per shaft, and we're going to use, and this is the way I drew it, we will use 4 blades per wheel. So this is we've got 4 arms of, each one of these is an arm. We have 4 arms on each wheel, and we have 3 blades on each arm. So each one of these is a blade. So we have 3 blades on each arm. Now the rule of thumb is that the total paddle wheel blade area on the shaft should not exceed 25% of the cross-sectional area. So again, this is a rule of thumb. This is not from the 10 state standards. It's simply a rule of thumb based on experience. And the reason is, if the area is too large, then you get excessive rotational flow, and you want it at least 15% to ensure adequate mixing. So the blade area per shaft is the width of the blade, I'll add, okay, times the length we calculated, times we have 3 paddles per arm. We have 4 arms per wheel, and we have 4 wheels per shaft. The typical width, I just calculated that, okay, is 10 to 15 centimeters. I've chosen an 11 centimeter blade, and that's what gives me this 15.05. Okay. And so now I want to calculate this ratio of my cross-sectional area of the blades to the cross-sectional area of my basin, and it's my width times my diameter because I'm looking at, because it's cross flow. So because it's the cross flow, I'm going to use the width times the diameter. And that is equal to 0.25 or 25%. So it's right at the maximum. Had I chosen a blade larger than 11 centimeters, or if I had chosen a 12 centimeter blade, I would have had excessive rotational flow. So I would want to reduce it. So basically, like I said, this is an iterative process. In reality, if you're doing this, you're going to pick maybe you pick 13, figuring it's kind of in the middle. And then you're going to have to do these calculations and then make a decision. Do you increase or decrease the size of your blades? So we now have, as I've drawn, okay, we've got these blades. We have what we're going to place the blade at the farthest point, okay, and then at 1/3 points. So we think I'm going to start with the outermost. So the outermost, the radius is 1.5, and then the center of my blade is at 1.445 meters. Okay, so here's the shaft. The radius, total radius is 1.5 meters. My blade is out at the furthest edge. So this distance here is 1.445 meters. Okay. I'm going to put the middle blade at a 1.0 meter, so I'm putting it at the third leading edge and then at 1/3 points. So this is going to be at 1 minus 0.11 divided by 2. So the center is R2. So this is this is R3. So R2 is 0.945, and this distance here is 0.5. So it's at the 0.5, and the center point then is 0.5 minus 0.11 divided by 2. So, okay, so this gives me R1. So now I have R1 and R2 and R3. Now, if you recall, when we did the same, we used this same equation for rapid mix. So what we're looking at is determining the water power required to achieve a G value. And we're just going to look at the first compartment. In reality, you need to look at all three. Okay. At 10 degrees, the viscosity is 0.00131 Newton seconds per meter squared. So for compartment 1, we have 50 inverse seconds multiply by the viscosity times the volume of the compartment. Why did I divide by 3?
Because that's the total volume.
Exactly. So this is our total volume, and this is the number of compartments. So so we need a power of 845 watts. The power input per wheel. So this is what I'm supplying to the shaft. It's actually more. Okay, this is the water power. The motor power is greater because of the inefficiency. You have 4 wheels. So the power input per wheel is 211 watts. The velocity, what I need to determine ultimately is I need to determine the speed at which these blades are turning. And all of your blades on that center shaft are going to be turning at the same speed because they're on that shaft. The velocity of the paddles relative to the water can be estimated from this equation right here. So this is the velocity of the paddles relative to the water. This K is a constant, and the 75% was stated early on, where we said that the velocity of the water relative to the paddles is 0.75. We have the radius to the center line of the paddles, that's what we calculated. We have D is the diameter to the center line of the paddle. So we can either do it in radius or diameter. And then we have the rotational speed. What we don't know is the rotational speed. This is what we're looking for. So we've determined the radius. What we don't know is n. And I'm going to write this in terms of n. Okay, so I'm determining each of those. I don't know n, so I'm writing my velocities in terms of n. Table 6-7 gives you design recommendations for a paddle wheel flocculator, and what it tells you is that if the length to width ratio is 5, then you'll use a coefficient of drag of 1.2. If your length to width ratio is around 20, then you'll use a coefficient of drag of 1.5. And if your length to width ratio is much greater than 20, then you'll use a coefficient of drag of 1.9. So we're going to use equation 6-9, which gives you the power imparted as a function of the coefficient of drag of the paddle. Since our length to width ratio is close to 20, we'll use a coefficient of drag of 1.5. Got the cross-sectional area, and this is equal to 4 times 0.11 meters times 2.85 meters. And the reason here is, here's our shaft, our paddle wheel. At each radius, we have 4 of these blades. Okay, so we have 4 blades. So that's why we're multiplying by 4. And VP is the relative velocity of the paddles. So we have the power as a function of the coefficient of drag, the cross-sectional area, the density of the water, and the relative velocity of the paddles. So we can write this, okay, since all of our paddles wheels have exactly the same area. So A1 is equal to A2 equals A3. We can factor out A, and we have here a sum of the velocities at each one of these sets. Jump down this on the side. So we have 211. That's what we calculated. So that was our power input to the water per wheel. So we previously calculated that, and that is equal to 1.5 times the density of water at 10 degrees C divided by 2 times 4 times 0.11 meters times 2.85 meters, the length, times 2.10 cubed plus 4.45 cubed plus 6.681 cubed, all times n cubed. Okay, so what I've done here is I've substituted in here back from here. So notice these are our V's here. They were all in terms of n. I've substituted in here, and I've just factored out the n cubed. So I can solve, and n is equal to 0.082, and that's in inverse seconds. So that's the revolutions per second. So if I substitute in here, so the revolutions per second are the same because the whole shaft is moving at the same number of revolutions per second. And the speed of my blade can then be calculated. So not surprisingly, the blade at the outer point, so this blade here, and this blade here, and that blade there, and this one right there, all have to move at a faster velocity than the innermost. because it's moving a greater distance. And the tip speed should be between, and this is rule of thumb, should be between 1.5 and 1 meter per second. And this is again from table 6-7 in the textbook, and we need that. We can calculate the maximum rotational speed in RPMs, and that is just the 0.082 revolutions per second. Multiply that by 60 seconds per minute. That is 4.9 RPMs. Typically, you're going to want a variable speed drive, and I'll answer that question in just a second. You're going to want a variable speed drive so that you can adjust your G value based on water quality. So we would pick a variable speed drive that would go from RPMs to from 1.25 up to about 5 RPMs. So the question is, where did the N come from? Go back, way back here. N is the rotational speed. We don't know what the rotational speed is. So what we determined here was that we determined the velocity of the paddles relative to the water is a function of this rotational speed. So then when we go to the equation for power, we have velocity in here, but we don't know N. We know the power, but we don't know N. So what we're doing is we substitute in for the velocity as a function of N. It becomes N cubed because velocity terms are cubed. And then we can solve for N. The minimum variable speed, okay, so we want typically you're going to want a 1 to 4 variable speed drive. So that allows you to reduce the G value. So you can adjust the speed once you design your system. So once going back, let's go back way at the beginning. Let's go here. Okay, once we design the system and we have everything in place, what can we change? Once we've built it, we've got everything installed, what parameters can we change? So we've built the system, it's in place, it's operational. I can change the rotational speed, exactly. So about the only thing I can change is the rotational speed. So if I'm changing my rotational speed, I'm changing the G. And remember, my G value is, we've got a maximum value so that we don't shear the flock. So if the only thing I can change operationally is the rotational speed, I want a variable speed drive so that I can adjust the rotational speed. So if I have a 1 to 4 variable speed drive, which is typical, then you'd have that would allow you to change your rotational speed from a 1.25 RPMs up to pick 5. Okay, so it's the maximum. Does that make sense why we would do that? The last thing is we need to size the motor. And typically your motor power will be 1.5 to 2 times the water power. So what we calculated, that P that we calculated, is the water power. It's not the motor power. So your motor power has to be significantly greater. So let's assume a motor efficiency of 60%, which is reasonable. It's right in that range. So that means that the power 60% of the power imparted by the motor is imparted to the water. You lose 40%. Some of it on heat, much of it on heat. So your motor power is driving the entire shaft is 845 watts divided by 0.6. So your motor, power of your motor is roughly 1400 watts. So when you're sizing your motor, you're going to have to choose a motor that produces significantly more power than the water power that you need.